stresses in rotating disc is in front of you. See, the fundamental equation which is used for this stresses in rotating disc is the equilibrium equation. Is it okay? So what is the equilibrium equation that you can see here? The equilibrium equation already in Cartesian coordinate system also we are familiar, and here in this polar coordinate system also we have derived this radial stresses, because equilibrium equations in three directions are different. In case of Cartesian coordinate system we are considering x direction, y direction and z direction, but in case of this polar coordinate system we are using the word that is r, theta and z. So r is the radial direction, theta is angular direction and z is vertical direction. Is it okay? So all these three directions we are taking into consideration in order to have the equilibrium equation. And from equilibrium equation in radial directions, whatever the findings we have got, so that is here, which is shown here. We can see that sigma r minus sigma theta theta upon r plus dou sigma r upon dou r plus 1 upon r dou sigma r theta upon dou theta plus dou sigma r z upon dou z plus fr is equal to 0. During this Cartesian coordinate system, if you are remembering, the equation was dou sigma xx upon dou x plus dou sigma xy upon dou y plus dou sigma xz upon dou z plus body forces capital X is equal to 0. So that was the equation derived in Cartesian coordinate system. Dou sigma xx upon dou x plus dou sigma xy upon dou y plus dou sigma xz upon dou z plus capital X is equal to 0. So that is the equation in x direction for Cartesian coordinate system. In radial direction, now if you will see, same thing is here, not different than that. If we look this particular part, you will come to know that dou sigma r upon dou r plus dou sigma r theta upon dou theta plus dou sigma r z upon dou z plus body forces which are indicated here it as Fr. In Cartesian coordinate system we are used to use the word as capital X, and capital X was the meaning that this was indicating the body forces. Here Fr, this notation we are using, this Fr represents the body forces in radial direction. Is it okay? Only the additional part which is present in this polar coordinate system is sigma rr minus sigma theta theta upon r. Is it okay? You will come to know here sigma rr minus sigma theta theta upon r. This is the part of the equilibrium equation in radial direction. So dou sigma r upon dou r plus dou sigma r theta upon dou theta plus dou sigma r z upon dou z. Here only the additional part is 1 upon r, which is get connected with this dou sigma r theta upon dou theta, and this is the additional part which is get connected as part of this derivation of this equilibrium equation in radial direction. Is it okay? Now whenever we are considering that this disk is rotating, and whatever the stresses generated during that rotating disk, basically the terms which are associated with radial direction, that only taken into consideration. Is it okay? So equilibrium, though this is the equilibrium equation, now we are going to consider only the part which is available in radial direction only. So the part which is in angular direction, the part which is in the vertical direction, so that is not taken into consideration here. So here you can see here that this 1 upon r dou sigma r theta upon dou theta plus dou sigma r z upon dou z. So this part is now neglected. We have considered only the part which is available in radial direction only, because we have to find the stresses in rotating disk in radial direction. So that's why, because whenever this disk starts to rotate, then we are familiar with the two kind of forces, out of which one is centrifugal force and another is centripetal force. Is it okay? So centrifugal force, which is the force toward the center and away from center, like this these two forces works. So always these are in radial direction, maybe towards center or away from center, but these two forces are definitely in radial direction. So that's why by considering only radial directions here, the terms which are not associated in radial directions that are neglected here. So dou sigma r theta component, which is related with this theta component, this is related. Another, this is the component which is related with the z vertical component. So theta and vertical, these two components are not considered here. So these two components which are neglected here, is it okay? So you can see here the arrow and 0 is written here, that means these two are neglected from this equation. And whatever the equation now we are taking into consideration, in that sigma rr minus sigma theta theta upon r plus dou sigma rr upon dou r plus body forces Fr is equal to 0. Is it okay? That is only taken into consideration. Now, by neglecting shear stresses and considering only radial stresses, is it okay? By neglecting shear stresses and considering only radial stresses, now the part Fr, already we have given the name to this part Fr as body forces in radial direction. So we know that whenever any body, any disk is rotating, then the centrifugal force mv square upon r, which we consider always, so which is considered here as a body force because the stress, this disk is rotating. Now with usual notations, the density is always given as density is equal to mass upon volume. We know the basic definition of the density as density is equal to mass upon volume. Then mass is nothing but density into volume. So here Vm, this represents the volume, rho represents the density, and m is the mass. Is it okay? So this mass m, this part here, this m is replaced with this rho into Vm, which is substituted here. So rho into Vm into V square upon R. Is it okay? Now if we consider this V is nothing but linear velocity, and we know that V is equal to R omega. Your 12th science, already we are familiar with this concept that V is equal to R omega. So this V is replaced by the R and omega here. Is it okay? So here you can see rho Vm, and this V is replaced by R and omega substituted here. Then this R and this R will get cancelled. Here we'll get rho Vm R and omega square. Here you can see that Fr is nothing but equal to rho. Here you can see. Then Vm R and omega square. One R has been cancelled here. Is it okay? Now if we put for unit volume, is it okay? So force, the radial force per unit volume, like this notation we are using. Then per unit volume means this particular part will get divided by the volume. So volume and this Vm, this term will get cancelled here. This body force now is shown Fr is equal to rho r omega square. Volume has been cancelled here. So body force is now Fr is equal to rho r omega square. Is it okay? So let us substitute this Fr is equal to rho r omega square here, and then we will get the equation that sigma rr minus sigma theta theta upon r plus dou sigma rr upon dou r plus rho r omega square is equal to 0. Is it okay? Now for this step we have multiplied by r. So for this step we are going to multiply by r. So once we multiply by r, then this r present inside the denominator will get cancelled with this r, and r will get cancelled here. Sigma rr minus sigma theta theta plus, now by multiplying by this r here, r into dou sigma rr upon dou r plus multiplying by this r, we will get rho r square omega square. Here you can see this r square. By multiplying with r, it becomes r square. So sigma rr minus sigma theta theta plus r into dou sigma r upon dou r plus rho r square omega square. With this it is multiplied, and then this step we got here. Is it okay? Now small adjustment we have to do here, and for that adjustment here you can see that if simply we try to write the multiplication r into sigma r, and if we take the derivative of that, what we will get? D upon dr of this r into sigma rho. So we are going to apply now the product rule. Is it okay? So r and sigma r, these are two functions, two variables, and we are going to apply the rule of derivation, product rule. And this product rule, first function as it is, derivative of second plus second function as it is, and derivative of first. Is it okay? So first function as it is, this is the r. Then derivative of second is d sigma rr upon dr. Second function as it is, sigma rr will remain as it is, and derivative of this r will become 1. So here the derivative of r into sigma rr, which is written in the form r d sigma rr dr plus sigma rr. See, here this was the first equation. We have given this as second equation here. Is it okay? So which is written in terms of their product. So if we come to this particular part here, r into d sigma r upon dr. So here you can see that this particular step which is present here with this, only we are trying to replace here. So r into d sigma r. So in this step you can see here, this is the part which is present here. Then secondly, sigma rr is also present here, sigma rr is present here, and this particular part, this r into dou sigma r upon dou r, which is also present here. So these two terms from these previous steps we are now going to replace with this d by dr. Is it okay? So here you can see d by dr. So if we substitute here, then what we will come to know, so d upon dr, which is substituted here, these two parts now which is present here, the sigma rr was there, and at the same time the second part which r into d sigma rr upon dr, which is present here, that both these both parts now can be replaced with this d upon dr r into sigma rr. Is it okay? So here you can see these two parts that are replaced with d upon dr r sigma r, because meaning of the both is same. First function as it is, derivative of second, and second function as it is, derivative of first. With this is replaced, this term is replaced by, and which is written in the form of derivation with respect, so derivative with respect to r, and this bracketed quantity. Is it okay? So remaining terms will remain as it is. So minus sigma theta theta plus rho r square omega square. Is it okay? Then let us put so r into sigma rr. Suppose this product r into sigma rr is present here, and one substitution we have made here. Let us make this small v as one substitution. So here we have substituted this particular r into sigma rr by this v. This small substitution we are going to make here. So this bracketed quantity is substituted with this variable and this v. Is it okay? Which is the product of this r into sigma rr. So which is placed here, remaining term as it is. Now take into consideration our regular notations through which we are identifying the strain. So sigma rr is equal to du upon dr. Okay. We know that sigma r is du by sigma rr, sigma theta theta, do all these things. So in a radial direction, we are considering the displacement as a u, and differentiation is taken with respect to r. So the strain in radial direction is given by du by dr here. Is it okay? Similarly, for sigma epsilon theta theta, that is the strain in angular direction. So for strain in angular direction, it is u upon r plus 1 upon r dou v by dou r by dou v by dou theta. Is it okay? Or dou v by dou theta, already we are knowing that how these strains are expressed. In case of epsilon xx, dou u by dou x, epsilon yy, dou v by dou y, epsilon zz, dou w by dou z. Like these notations we have used in Cartesian coordinate system. And now this is the polar coordinate system. For that, this epsilon theta theta is considered u upon r plus 1 upon r. For this also there are certain derivations, and with which it is come to this particular step. Now, as compared to u and r, because u is the displacement, r is the radius, and here the differentiation of this v with respect to theta. So this term will be very, very small as compared to this u and r, because r is the radius which is having certain value, displacement will also having certain value, but we are taking here the derivative of v with respect to that, and this will be very small, because the derivation process is the process through which the things go on, will become smaller. X raised to n is there, then it will become nx raised to n minus 1. Likewise, this will be reduced. So it is going to reduce, that's why this is neglected, this is a small part, and epsilon theta theta is considered to be u upon r here. Is it okay? So with this, u is equal to r into epsilon theta theta. So here you can see this multiplication is carried, and with this multiplication we got u is equal to r into epsilon theta theta. Now here it is differentiated with respect to r. Du by dr is equal to first function as it is derivative of second plus second function as it is derivative of first. Like this, we got here the du by dr is equal to r d epsilon theta theta upon dr plus epsilon theta theta. Is it okay? So like this, this epsilon rr, for that purpose already we have the equation. The terms which are associated with epsilon theta theta and epsilon rr, that now if we compare here, then epsilon rr is the differentiation of this u with respect to r here. Is it okay? Now here you can see that epsilon rr. So in equation 4, if we try to keep here, so this is the equation 4, and here's epsilon rr is nothing but du upon dr. Is it okay? So if we differentiate this u with respect to r here, then we will get the first function as a derivative of second plus second function as it is. So here du by dr, which is nothing but this epsilon rr from this equation 4. So that's why this du by dr is replaced by epsilon rr here. So epsilon rr is nothing but r into derivative of this epsilon theta theta dr. Whatever the right hand side of this equation will continue as it is here, and this left side, so that will be replaced by epsilon rr here. Is it okay? So epsilon rr is nothing but this term which is present here. Now we are making small modifications, but before going to small modifications, once again we are taking into consideration, so epsilon rr is equal to 1 upon e into bracket sigma rr minus mu into sigma theta theta is equal to, so this we know that from this strength of material concept or analysis, from analysis of mechanical element. आपण हा पार्ट बघितला होता. पॉइसन्स रेशोचा जेव्हा कन्सेप्ट आपण बघितला, इन केस ऑफ पॉइसन्स रेशोज वी हैव सीन दिस कन्सेप्ट हियर. So this whenever the condition, because here we are considering the r and theta directions, and this will become the biaxial stress condition. Is it okay? If it is uniaxial, we will consider only r, but biaxial condition in which r and theta both are taken into consideration, then the strain in radial direction will be considered to be 1 upon capital E into bracket sigma RR minus mu into sigma theta theta. Here you can see that this particular bracketed quantity. So sigma RR minus mu into sigma theta theta. So that things you have taken into consideration. Now here, and this epsilon theta theta, you can see here. Same thing is repeated here. As 1 upon E sigma theta theta minus mu into sigma RR. By considering biaxial conditions, we have considered this equation 6 and 67. Now let us differentiate this epsilon theta theta with respect to R here. We will come to know how this, after differentiation, this equation is present here. With this equation now we will continue. So here you can see in this last equation we got the differentiation of this epsilon theta theta with respect to this R, and we got this particular equation. Now we are going to put the equation 5, this equation 7, this equation 8 in this equation. So in equation 5, so 6, 7 and 8, what is present here? Epsilon RR. So for that epsilon R, we are going to keep this 6 equation in 5. Epsilon theta theta, for that we are going to keep this equation 7 in this equation 5. And at the same time, so this d epsilon theta theta upon dr, so this particular part which is present here in equation 5, that will be replaced by this equation. So this one will be, so all these three equations, so all these 3 equations now are substituted in this equation 5. So putting equation 6, 7 and 8 in equation 5, what is the sigma epsilon RR, what is epsilon theta theta, and what is d epsilon theta theta dr. And then we'll get, by substituting all these equations, because here we are getting 1 upon E, 1 upon E, 1 upon E, epsilon RR as sigma RR minus mu into epsilon theta theta, which is substituted here, and these common terms are cancelled here, and this equation is simplified. So after simplification, this E common factor cancel, and then we come to this particular point. This is equation number 9. So after substituting these terms and rearranging the terms, so after rearranging that terms, we will get 1 plus mu into sigma RR minus sigma theta theta is equal to R into bracket d sigma theta theta upon dr minus mu into d sigma RR upon dr. Is it okay? So this you can see. Previously here we substituted, because we have substituted already here. What is this R into sigma RR? So R into sigma RR is nothing but V. So that's why which is submitted here, and which is again taken the reference of this V is equal to R into sigma RR. So here sigma RR is nothing but R upon V. So this is equation 10, which you can refer here. And then this differentiation of V with respect to R here, dV upon dr. So we will get this is particularly sigma theta theta upon rho R square omega square. Here you can take the reference of that also. Here we have this particular equation. Same reference of this sigma theta theta, which is taken here. You can check this equation number 3, which is present here. So by taking the reference of this equation 3 here, what we are getting? dV by dr, or sigma theta theta is nothing but sigma theta theta. So dV by dr is sigma theta theta minus rho R square. With this, sigma theta theta is equal to dV by dr plus rho R square omega square. Is it okay? So let us differentiate equation 10, and then we will get that dou sigma R upon dou R. Let us now apply the U by V rule here. U by V rule of derivative will get R into dv by dr minus v upon r square. Is it okay? Because v into du by dx plus u into dv by dx divided by v square. Like this, we are using here this denominatorial term r into dv by dr minus first function v. Differentiation of r with respect to r will become 1, and here it is r square. Is it okay? So by substituting all these terms here and then cancelling the common terms, this equation 12 we will get. Then differentiate equation 11 again. So differentiating this equation 11, so this is the equation 11. So after differentiating this equation with respect to r, so d sigma theta theta upon dr is equal to dou to v upon dou r. With respect to r, it is differentiated. So after differentiating, we will get this as a term here. Dou sigma theta upon dou r is equal to dou to v upon dou r2 plus 2 times of sigma r omega square. Is it okay? Then as a next step, we have to do one thing, that is we have to substitute this equation 10, equation 11, equation 12, and equation 13 in equation 9 here. Is it okay? So this equation number 9, which was derived on the assumption on the basis of this sigma rr is equal to r into rho sigma theta dr. So with this, by this combination, by substituting these all equations here, what we will get? So we will get that v upon r. You see here d sigma theta theta upon dr. So for that, here 1 plus mu sigma rr minus sigma theta theta. What is sigma rr? Sigma rr is given here v upon r. What is sigma theta theta? Sigma theta theta is dv upon dr plus rho r square omega square. D sigma theta theta upon dr. So you can see this equation 13 is present here, and d sigma rr upon dr. You can see this equation is 12 equation is present here. So let us substitute all these terms here, and then you should just simplify them. Okay. So after simplification, all these terms here, this equation 14. So common terms are cancelled here, whatever the present. We get the equation here, it has v upon r minus 3 plus mu rho r square omega square minus r d2v by dr2 minus dv by dr. Okay. So after simplification, we will get this equation 14. Is it okay? So v upon r minus 3 plus mu rho r square omega square minus r dou square v upon dr2 minus dv by dr, which is equal to 0. Now here also small modifications, small alterations we are going to make. So this term is adjusted here. So how this term is adjusted here, you can see here the d upon dr v upon r. So again here u by v rule is used, and it is simplified here. So dividing r by equation this, we will get that v upon r square minus 1 upon r dv by dr. So this particular term is adjusted here, and it is simplified. So after simplification or dividing by this r, v upon r square minus 1 upon r dv by dr is equal to minus 3 plus mu rho r square omega square dou 2v by dou r2. So like this, small adjustments are made. It is divided by r, and this steps. Okay. Am I audible? माझा आवाज येतोय का?
Yes, sir.
Yes, sir.
Okay. So here dou 2v upon dou r2. So this small adjustment with this equation has been made, and here it is d by dr into bracket v by r plus dv by dr. So the right hand side minus 3 minus into bracket 3 plus mu rho r omega square. So that is present here. And then here one more step is carried, that is this equation is integrated. Is it okay? So after integrating this equation, what we get, v upon r is plus dv by dr, and this integration, for that purpose, what integration, minus into bracket 3 plus nu. So after integration, rho r omega square. So for this rho omega square, because this integration is carried with reference to r, so that's why this r remaining terms, this rho into omega square will become constant, and this r is r square by 2. Okay, so this r is r square by 2. Here it is C1. So like this, v upon r dv by dr is equal to minus 3 plus nu upon 2 rho r square omega square plus C1. This equation, which is considered to be equation number 16. Then once again, the small modifications is carried, small alternations are carried. So for that, this differentiation of this RV product, first function as it is, derivative of second, like this, the small modifications are carried here. And then these small substitutions are made here. Once again, it is integrated in order to have r into v. Once again this r, so by that r is this total equation is divided by this r in order to get the v term present here. And then once again resubstituting v is equal to r into sigma rr, because we know that we have substituted here that r into sigma rr is equal to v. So that's why again v is equal to r into sigma rr. So v upon r is equal to sigma rr. So that we can see here. So that is sigma rr. For that purpose, now here if you see in this we have substituted r into sigma rr. Then this r is transferred to the right side. It will come in denominator, and sigma rr will be equal to minus 3 plus mu rho r, because one r will get cancelled here, because here r square is present, r cube is present. So this r multiplied by which is present to the left side will come in denominator to the right side. One r will get cancelled here, and it will become r square. So rho omega square r square, C1 upon 2 and C2 upon r square. This will become r square because one r will come to this denominator, which is substituted otherwise with this v. V is replaced by r into sigma rr here. This r will come in denominator to the next step, and this will be sigma rr. So sigma rr will get like this. Is it okay? Now already we have seen that sigma theta theta is equal to dv by dr rho r square omega square. So whatever the equation we got here, sigma rr, so that is nothing but the stress, is it okay, which is considered to be radial stress in rotating discs. What is the stress in rotating disc? The stress in rotating disc is sigma rr, and which is nothing but into bracket minus 3 plus mu upon 8 rho omega square r square plus C1 upon 2 plus C2 upon r square. Now already we have this equation also, that sigma theta theta is equal to dv by dr plus rho r square omega square. So let us substitute once again the terms present here, and we will get the terms, because v term we know that here we have known this v is present here. So let us substitute here this v by taking differentiation here and by substituting the terms. So sigma theta theta we will get minus 3 into bracket mu plus 1 upon 8 rho r square omega square plus C1 upon 2 minus C2 upon r square. Is it okay? Are you getting these things? हे सगळ्या गोष्टी लक्षात येत आहेत का?
Yes, sir.
Okay. And now we are coming to this boundary conditions. So boundary conditions that will give the differentiation in two ways. That is, one is whenever the disk is with hole and whenever disk is without hole. When the disk is solid disk, there is no hole inside that disk. In that case, what will be the boundary conditions? So that now we are observing here. So we now got what is the stress in radial direction. Now we got what is the stress in angular direction. So angular direction and radial direction, that two stresses we come to know here. Now let us apply the boundary conditions here. So boundary conditions will say that when r is equal to 0, means that it's a center. When r is equal to 0, the sigma rr is maximum. Here at this value, the stresses will be maximum. So stresses in radial direction will be maximum at the center. So when r is equal to 0, but when this r becomes equal to b, means suppose in this particular circle, if this radius b part, this is considered to be b, this distance means if this radius is considered to be b, then at this outer stage, if we take this as outer stage here, at this outer stage, the radial stresses become equal to 0. Radial stresses are maximum at the center and it becomes 0 to the surface or periphery. Is it okay? So that's why when r is equal to 0, sigma rr is maximum, but when r is equal to b here, sigma rr equal to 0. So that is the boundary condition, and that boundary condition is applicable for the solid disk. So here substituted all the boundary conditions are substituted in this equation, because equation is like the sigma rr and sigma theta theta. So first of all, if we take the equation, so we'll get for sigma rr, it is multiplied by r square and small adjustments are carried, and the boundary conditions are substituted here. With this basis, C1 is calculated. On this basis, C2 is calculated. And then it is substituted. We get the sigma rr is nothing but 3 plus mu rho omega square upon 8 in bracket b square minus r square. Is it okay? Similarly, by substituting the value of C1 and C2, because here C2 is equal to 0, but C1 is equal to 3 plus mu rho b square omega square upon 4. So here sigma theta theta, value of sigma rr and value of sigma theta theta. So these two values now can be substituted here, and by substituting sigma rr and sigma theta theta, we will get these two stresses, sigma rr and sigma theta theta. So but this particular condition is the disk of, or this is the solid disk. Is it okay? So sigma r and sigma theta theta is combinedly given here. Is it okay? So in this case, we can see that how the stresses in this disks are identified. Is it okay? So stresses in rotating disk inside this, these are the stresses and how these are identified. So like this, you will come to know how to identify the stresses in a rotating disk. So anybody, any doubt? Anybody, any doubt?